right, so good morning, everyone. I'm happy to see such a busy crowd, even though Venkat's also speaking, so thank you very much for still coming to my little talk. During my talk, I'd like to guide you a bit through the road that we took at Picnic to make a decision to start using TimescaleDB. What different technologies did we look at? What competing options did we look at? Why did we actually choose it? And also show you a bit about what other options we also looked at in the past. And wrapping up with a nice small demo about what you can actually do with Timescale as well. So let me first tell you a bit about me. I'm Sander. I'm a staff engineer at Picnic. Funny story, last year I was also here at JFall, not working at Picnic yet. Got in touch with Sander Mak, who's actually there in the audience. Had a great talk, and yeah, 1 year later, yesterday I actually got a message on LinkedIn, hey, you are connected with Sander, and well, now I'm here 1 year later, actually working at Picnic. Before working at Picnic, I worked at a company that's called Infront Financial Services as a development lead. And Infront, really short, it's basically a company that involves a lot around stock trading, so the stock trading business. So a lot of real-time data and things like that. Besides loving to develop, I love being in nature as well. So that's why actually this picture comes a bit from me having good fun in Switzerland, being outside. So secondly, let's also just quickly tell you what's Picnic. I hope actually most of you know what Picnic is. But really short, Picnic is an online supermarket. We only have an app, so you use the app to order your groceries at our shop. And then we take care of your groceries. And we actually deliver them at your home free of charge in our small little nice EPVs. More specifically, what I actually do at Picnic. So I'm part of the supply chain domain. And supply chain domain is really everything from getting our groceries from the suppliers all the way up to our customers. And I'm really operating inside this whole area. So that's in short about Picnic. So first of all, I know the presentation is called Realtime. Me coming from the stock exchange business, Realtime means very low latency, like milliseconds, sub-milliseconds. In this case, it's not that real time. So basically, when we're talking about real time, in this case, it actually means near time, which just to state the picture a bit of what we're talking about. So what's actually the goal that we try what's the goal we try to reach with using Timescale? So at Picnic, we have a really awesome data warehouse where we store basically all of our data. It's huge. Only thing is that it's not data from now. It's basically data from 1 day ago, or at least data from the past, 24 hours. So that's really nice. We have that, really helpful. What we also have is data for the future. So we actually do a lot of forecasting. We really believe in a just-in-time delivery model. That's also part of our value that we really work towards reducing food waste. And that's where also just-in-time delivery, but also just-in-time ordering from our suppliers comes from. And talking about just-in-time delivery, actually this morning we just-in-time delivered our nice little EPV inside the venue. It was a bit late, but it should have been there at the first coffee break, so I hope you all saw it. But what's now our goal? So we have these things, we have this data to look in the past, and we have data to look forward. But we are still lacking a bit on data that we actually need now. And more specifically, data that we need now in our complete supply chain. And that's, of course, really relevant because for our operations, to make sure we keep to that just-in-time model, we need that data now. We need to know how are we doing. Are we doing quick enough? Do we have enough items in stock available? Do we replenish stuff soon enough? So replenish meaning that do we make sure that stock is available for someone to pick stock again when they need to pick it up? And to make this a bit more explicit, I have two small use cases as well. So one is about picking speed. And what we basically want is we want to know, so we have a warehouse, and basically in that warehouse we have people walking around. We call them shoppers. And these shoppers are basically the people that do the groceries for our customers. Instead of doing it for one customer at once, they'll do it for a couple of customers at the same time. And we really want to know, okay, but how fast are these shoppers? How quick do they do their job? But we also want to know is, for example, what products are they picking? And how quickly are products picked from different pick locations? To get a good overview of, again, okay, we have certain products that are being picked from the pick location, and we need to make sure we replenish these products in time. So knowing exactly now how fast we are picking, but also really on a product level, how fast are we picking products, we need that real-time information. With that, we actually also have a lot of data going on again. So looking at complete picnic, we'll have about 5,000 of these shoppers walking around at the same time. And we're doing over more than 1 million items that we pick on a daily basis. Not only do we have a lot of shoppers, we also do a lot of products. So we actually have around 10,000 unique products in our systems. And you can already hear it's quite big numbers, but it's also quite distinctive numbers. So 5,000 shoppers, 10,000 products. Going a bit further into that, we actually also, so these are some pictures of our automated warehouse. That's also a part that, besides doing just-in-time delivery, we really believe in automating everything. So we're also really acting as a tech company, as really, tech is basically at the core of our company. And so besides these pickers, there's also another use case. That's the part where this is more related to this automated system, where you see these little nice red crates there. We call them totes. Totes is really something, if you see picnic, and if someone opens their little EPV, you'll see the totes inside, the nice red totes. In our automated warehouse, we're basically handling about 40,000 of those totes on a daily basis. Again, in combination with the 10,000 products. And what we really want to know is, again, okay, how quick is this tote going around our system? How many articles are picked in that tote? What articles are picked in that tote? And we really want to know that on the tote level. So whenever we're talking about these operational, that operational information, we basically really want all the details. So we want to know what totes are there, we want to know what products are in there, but also a process that we do is allocate stock, so bananas, to such a tote. And that's basically an active process that we continuously do. And we also want to know, okay, maybe we are lacking some products at that moment, which we still need to replenish. So also that information, we want to know where for this tote, we're actually missing these products at this time. So again, we want to know all the details of these events, of the things that are going on. And taking these things into mind, we can dive a bit into what actually our requirements are. So first of all, as I started off with, we want to know all the details of the products, of the totes, of the shoppers. That means we're basically talking about high cardinality data. So it's not like, hey, we have 3 countries and country A, B, C, and if you only have these values, that's what you would call low cardinality data. And high cardinality data is you have a lot more of these differentiations in your data values. So that's for us really relevant to have that high cardinality data. A second requirement is that we really want a time series-like data. So because we want to know how we're going now, how we're doing now, but we also want to be able to, for example, display some charts that going back in time, not for ages, but at least for 24 hours to keep track of that whole speed of what we're doing. And also to, again, help a bit with, for example, on-the-fly forecasting that we want to do to make sure we replenish certain stock in time. So that's another requirement. Then next one is that at Picnic, basically in every team that we operate, we have analysts. Analysts that, for us, that basically help us even further improve our operations. So what they'll do is dig into our data. They'll do a lot of with our data warehouses, but we definitely also want to give them the tools and options to also do things with their real-time data that we get in. So what's the requirement is that whatever tool we choose, it needs to be accessible and preferably based on the technology that's already known by our analysts. So that's for us also really, really important requirement because they're really core of how we operate, how we improve or constantly improve our operations. So next up, quite obvious maybe, but it needs to be integrated with our systems, easily integrated. And with that, it's not only service-to-service integration, but ideally, I mean, we're not only talking about the daily operational data. We're also talking about more, you could say, the more detailed information about our things. So, for example, if you take a product, probably our operational data will just give you some nice number. Okay, it's a number. What you, of course, want to use with that in combination is, well, actually give me the name of that thing as well. So we're actually talking about bananas here, or about maybe some pasta. So that's actually some other data that I also see part of this integrating with Picnic systems. Then, last but not least, high availability. We're talking about operational data, and what we really want to do is, of course, make sure that this operational data is always accessible, as it will be there to basically drive our operations. So if this breaks, we'll have an issue. We'll basically going blind in our operations. So that's really important that whatever solution we choose is a high availability solution. Now going bit into the past of, okay, but you're not a new company, so basically Picnic exists for about 7 years already. Are you only starting with this now? Well, of course not. We actually did some attempts already. Partly, the attempts were based on how big we were. So we started off really small in Amersfoort, small company. In the meantime, we're actually operating in France, the Netherlands, and Germany. And we're pretty big in comparison to the small company we started up with at one point. So our first try was with a Ruby-based implementation called Dashing. I wasn't working at Picnic then yet, but I checked it, and this whole Dashing doesn't exist anymore. There's a follow-up, but don't use this. It's not there anymore. But it's basically Ruby implementation, and what we did is, via REST calls, basically call into our different services, primarily Java-based. And these services would actually not give you the feedback based on really the current state. But what we actually did is basically already aggregate the state internally, store that in a MongoDB, so that whenever this dashboard software would come by and do the request, it would basically just forward the MongoDB response already. So basically prepared metrics, you could say. It was really nice, looked nice, but had constant out-of-memory issues. It was running on a 32 gig machine, but somehow it just crashed and burned all the time. Not really helpful. By the way, they later figured out it was probably a sort of a memory leak in some JSON library used internally. Not an issue on Mac systems, but definitely was on AWS where we were hosting this. So yeah, it was not really helpful. So we tried again. Our next attempt, we basically ditched the whole Ruby stuff. And we introduced a Java-based service. Again, setup downstream was exactly the same. But now the Java-based service was introduced, and yeah, I tried to sort of, I hope this picture is clear, but I tried to depict memory. Just believe me, it's memory. And what we basically did is, yeah, do the same idea, question our services or query our services, get the information back, put it all in sort of in memory of that service. Really nice, worked pretty well, but yeah, not really scalable in the end, unfortunately. So again, nice try, but yeah, with Picnic constantly growing, it was not our ideal solution. So we tried again. The third one, again, sort of, we have a service in between, and we have our downstream services. I left out Mongo now for this time. I actually think we also switched a bit from the Mongo storage to just getting on-the-fly data in the meantime. And instead of keeping everything inside memory, we decided to basically use Postgres as storage here. Postgres is basically a database we use a lot at Picnic, so it's definitely known technology to us. So that's why we decided this way. And for visualizing, we actually went for an Angular setup, mainly because we had a lot of quite custom dashboards that we needed and custom views. So that's why we ended up with this. Again, really nice try. Oh, maybe one important thing, because what we also changed a bit was we're not only querying the service anymore, but we're also getting event-like data via RabbitMQ. So really getting more, okay, we're doing something in the system, push out an event, and in that way basically inform our dashboarding service that it happened. As I said, I already started, nice attempt, but not performant. Because basically we ended up with a lot of windowing queries in PostgreSQL. And yeah, especially with a lot of the amounts of data we were getting at some point, it sort of, yeah, you would have dashboards, but then worst case, I'll exaggerate, but worst case, you'll see what happened 10 minutes ago. Great, that's not what we want, so, okay. Next try. So next try was, again, different setup, Prometheus, which probably most of you know, where we use Micrometer to basically, as an abstraction layer in our services, to basically help Prometheus gather that information. And then on top of that, we use Grafana to basically visualize our data and visualize our dashboards. Worked really well, was performant, was scalable, but doesn't really support high cardinality. So again, okay, it's nice for let's say your basic metrics, for some counters, for some gauges, but it just didn't really suffice for what we wanted at Picnic. So that's why we had actually now ended up at the start of our story. Okay, what do we do then? We tried these. So first of all, we tried looking into some full-blown metrics support solutions. We looked at New Relic, Wavefront, Datadog, Honeycomb, Splunk, all the bus metric systems you could say that are out there. And even though they're quite interesting, they were still a bit limited to what we actually want, because all these systems are very much focused on just taking care of your metrics. But yeah, with all part, for example, of integrating with Picnic data, basically being able to model your data a bit more that you are storing and that you want to keep track of, it didn't really suffice our use case. We basically want to be able to get more insights in our data in comparison to what these solutions would actually be able to give us. So yeah, basically that made us decide, okay, maybe we shouldn't look into these real metrics-like solutions. Maybe we should look more towards some kind of a time series database. So that's what we end up doing next. So we started looking at some. First there was InfluxDB, which is actually quite a popular time series DB. Should have quite good performance. Looked promising. But if you start looking into the details, you actually see that they don't really have good high cardinality support. Basically, their advice is to, if you want high cardinality, change your data model, which is not what we wanted, so not really helping there. So we also looked at Druid. Again, also quite an interesting solution. Also looked sort of promising, but it actually has the same issue as Influx, no high cardinality support. Next one, Victoria metrics. Same story, unfortunately. So all of them were sort of, yeah, you could say, they're just not fit for what we needed. So we started looking further. We looked at Amazon TimeStream. Looks promising. It's from Amazon. It's basically running on their platform. It's sort of a serverless setup. From the ingress speed, it's a bit questionable. They seem to be really good at IoT-based situations where you have a lot of different small devices basically sending data. That should work pretty good. Seems to work not so good for example, one service which wants to pushes in a lot of data. Seems to be less suitable for that. But also when looking into it, it's a bit too much focus for metrics again. So maybe should actually have been part of the previous slide. But we took this into account for our time series database research. So also that was not a good fit for us. Then another option we found is CreateDB. Very good performance, high cardinality. Actually allows you to do some data modeling. So sounds very interesting. Unfortunately, literally checking from their website basically, if you end up in a situation where you would like to do quite some separate tables, some separate joins, it's not a good fit. Taking into account one of our requirements, so integrate with picnic systems, we basically decided, okay, we'll probably run into issues with this specific remark. So still no good solution for us, unfortunately. So we ended up looking further. I assure you can probably look for solutions and find solutions for until you grow old. I mean, there's a gazillion solutions, as we all know. But we ended up actually finding two, which sounded very, very interesting, which is Timescale and which is QuestDB. And Timescale and QuestDB, they're both actually time series databases. But we'll look a bit more into detail of the both. So first of all, QuestDB. So QuestDB is a solution that's completely built from the ground up, completely not based on anything. And it's a column-based database. So in comparison to, for example, Postgres, which is basically row-based, the column-based database, usually fits very good for if you want to really do analysis on your data. So that's a bit of a difference, for example, to Timescale, but we'll get to that a bit later. It has support for high cardinality data, so definitely good need for that. What's really nice is that even though it's built from the ground up, it actually supports Postgres compatible SQL. So as Picnic is really a Postgres-oriented company, that sounded really good. That sounded like something, okay, then probably our analysts can also really work with that. And furthermore, as it's a time series database, it has a lot of specialized time series functions. So with functions like that, you should think about, for example, time buckets that you need. So I have my data, but I want to display a nice chart of it, or a nice graph of it. So I'll take, I basically split my data into time buckets of 5 minutes, for example. And every bucket, I can count the values that are there. But what I can also do is for that bucket, check out what's the first value and the last value in that bucket of my specific value. So it's something partly related to the stock industry, for example, where you have these open, low, high, close charts, sort of bars with a beginning and end. So that's also something you can do with time series. Histograms of your data. So basically, data related to that. So all very interesting options, which definitely made QuestDB a good opponent towards Timescale. So let's look at some of the features of Timescale. So Timescale is actually by itself, it's not built from the ground up, it's actually an extension to Postgres. So again, for us, big Postgres user, already made it very, very interesting in that way. Yeah, where I said that QuestDB is a column-based database, Postgres is actually a table or a row-based database. It also has support for high cardinality, basically like Postgres also has by itself already. It uses, because they have the marketing terms, I use them in here as well, but they use hypertables, and that's actually the core of what they actually do. So what a hypertable actually is say you have a table with time series data in it for a year. If you just put that in a single huge table, you'll probably run into some performance issues when querying the data. What these hypertables actually do is they split up the data. So you can actually say, okay, please take this time series data set and split it up in chunks of 1 month, for example. And that's actually also the trick that time series applies, that they don't have this one huge big table, but they just have different chunks or shards in which they divide the data. And in the basics, it's basically time series based, but you can also actually add additional partitioning. So what you can actually say is, okay, I have, well, let's take 3 countries again. Then you can actually split it up in chunks for the time rate, but also in additional chunks for these different countries that you also have. And what's really nice is that they actually built a distributed model of that. So meaning that it's not running on a single node, but you can actually scale these tables up in multiple nodes. Meaning that, hey, maybe your January data is on node 1, and your February data is on node 2. And that will actually allow you to parallelize your queries over multiple nodes if you need to query that data. So that's quite a fancy feature. Another thing they have is continuous aggregates. And that's basically, thinking about dashboards, what you probably normally have is that you have a lot of dashboards, and you probably have a lot of people looking at the same dashboards, but on different machines. If you just end up querying that data all the time, it means that all these consumers will basically aggregate the data all the time, each separately of each other. So basically, could have quite an impact on your system. But with continuous aggregates, you can actually pre-calculate that aggregate data, meaning that only the database server itself will basically take care of aggregating the data, but the consumers, they just query that aggregated data source. So we'll basically reduce the power that you need for your machine by a lot. And what's really nice is that they do it for all your historical data, but even if data is not even stored on disk yet, so it's basically still it's part of a committed transaction, but maybe not still in flow, it will also take that with its final data set as well. So it's really optimized, making sure that you get the last data that came in. The another thing is, sorry, it's again the marketing term, but hyperfunctions, basically time series related functions. So like I just said, the time buckets or the aggregation of data, getting open, low, high, close data, all these functions, they call them hyperfunctions, but in the end it's basically functions to request your time series data. A lot of helper functions which makes your life a lot easier in comparison to if you try to do that with a normal Postgres database. And one thing as well, data compression. What they tell you on the website, I didn't try it, I don't really believe it, but they tell you they can compact your data with 96%. Sounds to me like a bit exaggerated, but at least taking into account that whole data compression part, what you can basically do is, hey, I have this table, and please compress my data for me. And maybe 96% is quite a lot, but at least you should expect quite some wins there on the amount of storage capacity that you need for this data. It's actually, what you can actually also do is indicate what data should actually be compressed. So you could also say, okay, old data in these old chunks, compress that, and new data, please just leave that as it is. I mean, I didn't test it, but I could imagine that maybe there's a bit of a performance difference between compressed and uncompressed data. But that's also what they basically just have built in to the system. So now we get to the big show-off. What makes sense? What fits our needs of these two competitors? So high cardinality, I actually already talked about that in both solutions. They both just nailed that. So no issues with that. That works. Time series data, also good plus. Our analysts, as I said, avid SQL users, they can definitely work with this. They don't have to learn anything new things, maybe some time series related functions, but besides that, they can basically just use the language that they know. So that's really a big plus for that as well. Integration with picnic systems, that's also a big plus because, I mean, for Timescale, definitely, it's just Postgres, so with some special functionality. For QuestDB, as they basically support the full Postgres SQL setup as well. You basically have the required functionality there to model any data that you want in it as well. So basically means that both solutions will give us full flexibility in what we want to do. And last one, finally, we can get to an answer. High availability. Because Timescale has high availability. You can just run multiple nodes. And for example, in a cloud environment, they will just completely take care of it for you. Also directing your entrance to whatever node's active. So really good. QuestDB doesn't have that yet, unfortunately. They're working on it, but yeah, it's not there. So for us, that's really a big reason to say, okay, QuestDB is an interesting option. And I still believe that. And that's something, let's say, we'll put that in the category one to keep in mind. So one to track also going into the future. But for our current needs, unfortunately, it's not really what we want. But the good part of not having high availability means that we could make a decision. So that's really cool, because that meant we could choose for Timescale. So just some more arguments for the final choice. It's picnic node technology, using a lot of Postgres. It's just an extension, you install it, so we know this. We know what we do with it, so very helpful. It has high availability. What's really important, and this may be partly in combination with that high availability, it has a more mature cloud platform. I need to make a side note on that, because also Timescale Cloud is not that mature yet. So it runs stable, it runs good, it runs in high availability. But what, for example, they are now still lacking is the ability to automatically operate your environment. So, for example, Terraform support is not included yet. They're going to include it, but it's not available yet. However, comparing that to the cloud platform of QuestDB, while doing this research, after our research, I got an email from them. Hey, we're very happy. We just started with our first cloud customer. So, yeah, I think it was a good decision on that point. Next one, very extensive documentation. So that's also actually, if you look at the comparison between QuestDB and Timescale, QuestDB, I could hardly find any documentation, to be honest. So I think they definitely need to make some steps there. For Timescale, it's extremely extensive. They're describing everything, have a really nice lot of examples. So for you as a developer, it's extremely helpful to just get started, get into it straight away. They have a lot of examples to just, hey, you want to try it out? Here's your sort of 1-minute description. Have fun with it. So, and that's really, really helpful. They also have a really broad range of different time series functions. So they actually have more than are available in QuestDB at the moment. I'm sure they'll catch up at some point, but yeah, there's really tons of different time series functions. Yeah, integrates well. Basically said it already. Okay, so now let's just look at how do we actually use it at Picnic. What setup did we come up with? So what we basically do, it looks partly a bit the same as the other pictures, but we still have our nice Picnic services. They didn't go away. And we still have RabbitMQ to basically feed the data. You could basically draw a second arrow with, we're not doing that yet, but a second arrow with Kafka to also get data from Kafka. Then what we did is we built a collector. And the collector basically collects events from Timescale, from RabbitMQ, does any requirement transformations that we need to do there, and then pushes that to Timescale. So that's basically our int feed into Timescale. Now optionally drawn, but what could happen is that we still have some REST calls to our services, basically to enrich our data a bit more of what we store in Timescale. Then looking at the actual consumer side. So on one hand side, we have Grafana. And what's really nice is that because Timescale is also just an extension on Postgres, you can just use the SQL plugin that comes with Grafana to just say, okay, use this query to select my data from my database, and then draw really nice charts of that. So that's really easy. So we use that for quite some of our dashboards, and to show quite some of our data. What we also have is that for some pages in our systems, we want a bit more advanced querying. And we want integration with data coming from one system and from other systems. So for that, we actually have a separate querying service, which does the heavy lifting on the querying side, for where we really need integration in some of our other services. And even though it's the same Angular logo here, it's actually not really necessarily a dashboard here, but it's more the operational systems that we use in our warehouses, which is also Angular-based, which people then just use and not only show data from the actual source systems, but also show these time series data. Then also some charts. They're not, well, they look okay, but just it's a bit to show you the high cardinality data part in it as well. So basically that little slide there, that's just the picking speed. So one of the use cases. You see actually picking speed, I think between different warehouses, how quick we are. So that's actually not really high cardinality data yet, but especially the top chart, but also the left bottom chart. So what you actually see there is information about products that we currently cannot pick. So because they need to be replenished. They're not available at the moment for someone to pick. And that's a big difference in comparison to, for example, the Prometheus solution, which we had earlier, where we just couldn't show this, actually. So we knew that, okay, we are missing some articles, but we had no clue which ones. And now we can actually, down to the product level, just indicate, okay, we're missing these, and these. And that really helps us to support our operational business and make sure we can really keep that just-in-time model in place and know exactly what's going on and what we need to act on. So yeah, that's really, really great outcome for us. And now I have a small demo.
Quick question?
Yeah, sure.
Maybe I missed it. What's the last arrow back to the server?
This one? Yeah, so that's what I meant with the Angular solution here. So that's basically, you could say, it's sort of the operational, basically the system we use to modify things in our warehouse systems, or to, for example, you have these totes. We can show a page there. Okay, these totes are in the system, and the metrics for, hey, what's actually the state of this tote? We'll get that via that querying service. But to actually know about the tote itself, we need to go to the source system, basically. So that's what the error was. So good question, because I think I didn't really explain that, but that's what the error was doing there. Cool, so let's do a small demo. Hope this works. So I prepared a small demo set. So if we look at this, what we basically have, I've created 3 tables, one for articles, one for shoppers. I didn't take the most exciting names, but just a use case. And we have pigs. So pigs meaning that a shopper, table 1, picked an article, table 2, and with a certain amount. So 5 pigs, 3 pigs, 4 pigs. And this is basically the data set. Just to give you a bit more view on, okay, what are we talking about? So it's actually a data set for October, and it's almost 2.7 million records. So what I basically did is, from start of the month to end of the month, for every second, generate some data. So that's our data set. Now, it's now still just a regular Postgres table. So nothing magic going on yet. But now what I want to do is create a hypertable of it. You can either do that upfront, or you can do that for an already existing table, which is basically this migrate data flag that tells you, okay, I already have data, so please take that into account as well when you generate this table. So I'll just start this, and what I'm basically doing is indicating this is my table that I want to transform. This is my time column, so event time. That's basically the time column that I introduced. It can either be a time zone. I think I use time zone TZ here, but you can also, it actually also supports more integer-based or timestamp-based time zones, time indications. And what I do is I indicate a chunk interval of 1 week, meaning that for every week, I'll get a separate data chunk or a separate data table in the back. It does take a bit of time, as you can see, but yeah, still 2.7 million records, which needs to be crunched here. So there we go. Then if we look at, just to show you these chunks, so there's actually some helper functions. Here you can actually see that, hey, these are the different chunk tables that were created. As you can see, it's not 5 nicely even weeks. I mean, there's a bit of the end, a bit of the start. But we ended up with 5 different chunks of data. So really meaning 5 different files that we store. And you actually have a lot of control to also indicate where do I actually want to store these chunks. So you can actually even distribute it on different disks. And with a distributed model, you can even store it on different nodes. So that's pretty nice. So now we have our time series data, or time series table. So now we want to try out some of these hyperfunctions, of course. So first of all, there's the time bucket. So I'm making a time bucket of 5 minutes based on the event time. And I'm basically querying the average amount of articles that are picked by a shopper during that time. There we go. So what you see is that we have here, just scroll down a bit, so you'll see different, yeah. So this is the first set of time buckets, and then comes the second set, each with 5 minutes intervals, basically. And then for each shopper, we have the shopper name, and then, the average amount that it will pick during this period. So that's the time bucket. Then we have a first and last. So I'm actually getting that from last day of the month. What I'm basically doing is, okay, for this shopper, check out when his first pick was, when the last pick was. they work 24 hours at us at a picnic, as you can see. And basically also, yeah, give the information about what's the first article and what's the last article that was picked. And max and min are really easy for the time, but last value and the first value, what actually mixes up, or is assigned to that event time. That can be a bit more complicated to query, but with first and last, it's super easy. Just say, okay, I have this time range, give me the first value, give me the last value, done. So also for these stock charts for open, high, low, close, you can also really easily use that. Then we have a histogram. So this is basically, 0 is always there, but basically no one has 0 counts. But this is basically distribution per hour of, okay, how many picks of 3 items, how many picks of 1 item, how many picks of 2 items were made by these shoppers. So that's also really nice overview. Then another thing is gap filling. So if you have time series, a lot of times you want to show some charts, but maybe not all data is there. That's called a gap. And if you don't fill up these gaps, a lot of times you end up with very strange looking charts, which you don't really want. So what I'll do is just remove some of the data that we had. And I'll just first show you with the normal time bucket. And what you can see here, we have quite some gaps here. So 11:45 to 12:15. I deleted that, but it's also, that means that in your final series, you're actually just missing this data, meaning that you can really have issues with your charts that you want to draw. But if you use the special gap fill function, you'll see that these gaps will get filled up. I left the nil there explicit just to show you. You can, of course, always replace it with a different value. But you see that this really makes sure that for each of these data points that we expect a record, it's actually there. So that's really nice gap filling functionality. Then last part, and we're almost done with the time, so quickly. So this is a small demo of continuous aggregates. What I'll do is on a daily basis, I will basically collect for each shopper how many picks that shopper did that day. So we'll create it. Now it's there, and we can basically now query that continuous aggregate. There we go. So this is the data. Just to show you the real timeliness sort of, I'll add some more data. Oh, I'll first show you that our last data point here is, oh, there we go. Basically the end of the month, as you can see, with one data point that sort of slipped through. But if I add some more picks to it, just generating for a new day, yeah, there we go. Then if I run this again, you can already, we go to the last part, you can actually see that, hey, it's already there. So it's just on the fly, your continuous aggregate is updated with new data. And what's also really nice, last feature that I'll show, is that Timescale also has a retention policy. I mean, how often is it not that you have this data and at some point you just don't care anymore? You don't need it anymore. Or even more important, you have detailed data and after some time you don't need the detailed data anymore, but you can do with some aggregates of it. And that's what I'll show you now. So if we look at what we have here, so this is again small view of our continuous aggregates, start time, end time, number of records. And if you look at the picks, like we did before, yeah, basically October with some additional days now. Now, what I'll do is add a retention policy to our source table, so the picks table, saying, hey, please just drop everything after 1 week. I don't care anymore. So if I run this, then what you see, if you look at the picks table, we have much less data. So suddenly it's from the 27th and not all the way at the start of the month anymore. So automatically it just drops the data for you. Really, really handy. So you don't need to write any cleanup processes for that. And the nice thing is, if you now look at our continuous aggregate, it's still there. So that's really nice to build cleanup mechanisms for all the data, where you just need less detailed information. And with that, I'm done, because there's the end point. Thank you very much.